Okay, so I call this section tricky trig integrals. Your book just calls it trig integrations. There's special integrals with special trig situations going on, and there's two parts to it, and I have a feeling that each section is going to be a separate video. So I have my first part that has the integrals of the form sine to a power times cosine to a power. Okay, so for these problems where we can't do a traditional u-sub to fix the fact that I have a composite and a product, I'm going to use our identity, that sine squared plus cosine squared equals 1, and the power reducing formulas, that sine squared is 1 minus cosine 2x over 2, and that cosine squared is 1 plus cosine 2x over 2. The same power reducing formulas that we used for polar curves. Okay, so the rules are, if the power of sine is odd, we save one sine for a u-substitution, and we convert the remaining sine terms using the identity. If the power of cosine is odd, we save one cosine for a u-substitution and convert the remaining cosine terms using the identity. And if both sine and cosine have even exponents, we use this should be power reducing formulas. Okay, so if both sine and cosine have even exponents, we use the power reducing formulas to get an odd power of cosine. We save one cosine, convert the rest as above. Okay, so I know that sounds like a lot of mess, but let's look at some problems and see what's going on. I had some students a couple years ago come up with some, I guess, tricks to kind of help you remember. Okay, but the focus is that whichever trig term is odd, okay, we're going to save one of those and get rid of the rest. So if sine is odd, we save one sine. If cosine is odd, we save one cosine. And if both are even, it's like polar curves. Okay, so let's look at some problems. Okay, so let's start with the integral of cosine cubed x dx. Okay, now we should realize that this is a composite function. We cannot simplify the composite at face value. If we try u-sub, if we let u be cosine, our du is going to have a sine in it, and we don't have any signs for a du. Okay, so we have an issue. All right, and that's why I call this stuff tricky trig, because you're kind of doing things that you'd never think of to do with a problem, so that you can have a way of integrating it. Okay, so we said in the rules that if the power of cosine is odd here, which it is, I'm going to save a cosine term. Okay, so I'm going to take out a cosine term. What would I have left if I take out a cosine term? I'd have left a cosine squared. So I know it's going to be awkward to write it this way, but I'm going to write this as the integral of cosine squared times cosine x dx. Okay, so this is the cosine term that I'm saving. Okay, so I'm pulling out a cosine term and I have whatever's left. Now I said that the whole point of this is so that I can do a u-sub because I have a composite. I need to do a u-sub, but I had nothing for a du. Okay, so whatever I'm saving is going to be for my du. So okay, so that cosine part is for my du, which means my u is going to have what in it? Think about that if you need to pause. So what does my u have to have so that I'm going to have a cosine in my du? Okay, in order for my du to have a cosine in it, my u is going to have a sine term in it, okay, which is going to mean that this is going to foul me up. So the whole point is to use something to get rid of a cosine squared, and that's why I mentioned the identity in the first place. Okay, so we know that sine squared plus cosine squared equals 1, so I'm going to have to get rid of cosine squared using that identity, and cosine squared would then be 1 minus sine squared. So what I'm going to do is I'm going to rewrite this integral as the integral of, instead of cosine squared, 1 minus sine squared. And that cosine x dx at the end, I'm going to save that for my du. Okay, so now, okay, so we're going to let u equal sine x, all right, and just like we said, the whole point is so that my du has a cosine x in it, so du would be cosine x dx, okay, and then when I make my substitution, I'm going to have, and if you want to go ahead and do it, just pause the video and come back to me when you could finish the integral from here, or, you know, whatever. Why don't you try to finish the integral? Pause the video, come back. So I'd end up with the integral of, if u is sine x, 1 minus u squared du, and when I integrate, I get u minus u cubed over 3, and then I'm going to plug back in, and if I plug back in sine x in place of u, I have sine x minus sine cubed x over 3 plus c. And there's my answer. Okay, so we took a problem that was non-integrable because I couldn't u-sub away the composite, and by taking out that term, holding on to that term, I was able to make a substitution and do a u-substitution that was functional and get an answer for the integral. Let's look at another example. Okay, so I have the integral from 0 to pi of sine squared x dx, all right, and you guys have exposure to an integral like this because of our work with polar, so you really should be able to do this on your own, but again, for sine and cosine, you're looking for whichever trig term is odd, or if you have only even functions, then you use those power-reducing formulas. So we're going to use a power-reducing formula on this, and because it's sine squared, we're going to rewrite this as, just as a reminder, sine squared is 1/2 times 1 minus cosine 2x, so this integral becomes the integral from 0 to pi of 1/2 times the quantity 1 minus cosine 2x dx. Okay, so with this new integral, we still have a composite, right, where cosine 2x is still a composite. I'm going to do a full u-substitution with change of bounds. So my u would be 2x, and then du would be 2 dx, and because I don't have a 2 dx, I'm going to have an extra 1/2 as a coefficient out front. So my new integral will look like, I'm going to have this 1/2 here, okay, and then from my du being, or my 1/2 du being dx, I'm going to have another 1/2 there, okay, and then instead of having 1 minus cosine 2x, I'm going to have 1 minus cosine u, with my du, and then I changed my bounds, so u is 2x, so my lower bound was twice 0 or 0, my upper bound was pi, now it's twice pi or 2 pi. Alright, then I'm ready to integrate. So I will have 1/4 times the antiderivative of 1 is u, minus the antiderivative of cosine u is sine u, and I'm going to go from 0 to 2 pi. If I do upper bound minus lower bound, I will have 1/4 times 2 pi minus sine 2 pi minus 0 plus sine of 0, which is going to give me sine of 2 pi and sine of 0 both 0. So I have 1/4 of 2 pi, which is pi over 2. Alright, and there's my answer, just a refresher on what we did from polar curves. Let's look at another example. Okay, so for number 3, I want to do the integral of sine squared x times cosine squared x dx. Okay, and the main rules are that if there's an odd term, you save one of those, well, if there's an odd power, you save one of those terms. These are both even, so we're going to follow that third rule, okay? So I have to make my conversions using my power-reducing formulas. Okay, and I need to get rid of every term that has an even exponent. So I'm going to have to use both power-reducing formulas in this situation. Okay, it's a weird situation. So go ahead and pause and replace both sine squared with its power-reducing formula and cosine squared with its power-reducing formula. And after you've made that substitution, come back to me. Okay, then this looks pretty awful, but sine squared is 1/2 times 1 minus cosine 2x, and cosine squared is 1/2 times 1 plus cosine 2x. Okay, my next step on this, because it's a product of things and it's just a big hot mess, is to simplify it. So go ahead, pause the video, try to simplify this, think FOIL, and come back to me. And what you should have gotten is a 1/2 times 1/2 gives you the 1/4, and if I FOIL out the 1 minus cosine 2x and 1 plus cosine 2x, my outers and my inners will cancel. That's not true. Yes, it is. Okay, so I end up with just my first minus my last squared, so I get 1 minus cosine squared 2x. Okay, if you look at this closely, I still have a composite. Okay, I have a cosine squared 2x. And if you think about that, that's just like our polar curve situation. I have an even power of cosine. I have nothing for a du if I do a u-sub. So I'm going to have to use one of those rules that we just came up with, okay? And I don't have any odd powers of trig, so I'm going to have to use my... Okay, so we're going to have to use that power-reducing formula all over again. So I'm going to have to make a substitution on cosine squared 2x this time. So remember that... when you reduce the power, you double the angle. So cosine squared x became a 1/2 times 1 plus cosine 2x. So what would cosine squared 2x become? Pause, try to make that substitution, and come back to me. Okay, and I pulled the 1/4 out front. Okay, I have my 1 minus, and instead of having cosine squared 2x, I have 1/2 times the quantity 1 plus cosine 4x. Okay, I'm going to simplify this. I'm going to distribute through this 1/2, and then I'm going to combine like terms, which I'm going to have up front here. So go ahead and do the same thing, and pause and come back to me. Okay, and when I distribute through, I'll have a 1 minus 1/2, which gives me a 1/2, and then a minus 1/2 times a cosine 4x, which is my minus 1/2 cosine 4x. Okay, so now that I finally have a cosine to the first power, I can do a simple u-sub to get around the composite over here. I'm going to do that u-substitution on the side and then come back because there's just too much going on here. So I'm just going to focus just on this piece for a second. So figure out what the changing coefficient would be with that u substitution. Pause it and come back to me. So we're going to let u equal 4x. That would make du equal to 4 dx, which means we really have the integral, instead of cosine 4x, I'd have the integral of cosine u. Okay, and then because of the du being 4 dx, my dx would be a 1/4 du. So the integral of cosine 4x, I'm just looking at this part of it, would be a 1/4 integral of cosine u, and that would give me 1/4 sine of u. Okay, so I'm going to put that 1/4 sine u in place of my cosine 4x when I integrate. Okay, so if you need to go back, pause me, finish it up, come back to me, go ahead. Alright, so this is what you should come up with. I have my 1/4 coefficient, it's staying out front. The antiderivative of 1/2 is 1/2 x. I'm holding this 1/2. This 1/4 coefficient is right here, and the antiderivative of cosine 4x is my 1/4 sine u, and the u is really 4x, so I have 1/4 sine 4x from the u sub. Okay, if I go ahead and simplify this, just distribute and combine my coefficients and stuff, I should have 1/8 x minus 1/32 sine 4x plus c. Okay, a little messy with all those coefficients and the u substitutions. I did really a worst case scenario problem with these even exponents, but I figured it'd be better to do worst case together than to just assign you a horrible one on your homework without ever seeing anything like this before. So hopefully you won't come into contact too much with problems that are this messy, but really that's all it is. It's messy. It's not hard. It's not crazy. It's just, well, it's a little crazy. It's just really messy. Let's look at another one. Okay, we're going to do an ugly one together, and then you're going to do a simpler one on your own, okay? And we'll talk about the next one in class tomorrow. So for number 4, I want to do the integral of cosine to the 5th x times sine to the 4th x dx. Okay, so again, we're looking primarily for odd exponents, and if we have an odd exponent, which I do here with my cosine, I want to save one of those terms at the end. So rewrite this, pause it and rewrite it so that you have a cosine term lingering at the end of your integral, and see what's left. And come back to me when you're ready. Okay, so when you save that cosine at the end, you should be left with the integral of cosine to the 4th times sine to the 4th x times cosine x dx. Okay, and the whole idea is that whatever you save, I know we just did 2 even problems, even exponent problems, but with this odd, you save one and you get rid of the rest. So I need to get rid of this cosine to the 4th. Now the problem is my identity is for cosine squared. It's not for cosine to the 4th. It cannot be applied to cosine to the 4th. So I need to have a cosine squared here. So think about that. Pause if you need to, and think about how I can get a cosine squared there. Okay, and what I can do, hopefully you realized it, is that I can write cosine to the 4th as cosine squared squared. Okay, and once I have that as a cosine squared, I can make that substitution. So remembering that sine squared plus cosine squared equals 1, cosine squared would be 1 minus sine squared. So make that substitution, pause it, and come back to me. Okay, so my cosine squared becomes 1 minus sine squared. So I have 1 minus sine squared quantity squared times sine to the 4th x times cosine x dx. I'm actually at this point ready for my u sub. Okay, I don't want to try to FOIL that out right now because it's a big mess with that trig, but if I make the u sub first, then I can simplify it. It won't be as bad. Okay, and remember the whole point is that what you're saving at the end is for your du part of your u sub. So what's my u going to be? Think about it. I'm going to have u be sine x. Okay, and then my du would be cosine x. Okay, so go ahead and make your u substitution and come back to me when you're ready. Okay, and I should have come up with, instead of having 1 minus sine squared, I have 1 minus u squared, quantity squared, times sine to the 4th is really u to the 4th, and my cosine x dx is my du. All right, at this point, now that I have my cute little u's, FOIL that out, combine all your like terms, pause it, come back to me. All right, we can't integrate a product, that's why we have to do that. So do that and pause it and come back to me. So when you FOIL it out, you should end up with 1 minus 2u squared plus u to the 4th times u to the 4th. Multiply that through. You end up with the integral of u to the 4th minus 2u to the 6th plus u to the 8th. Integrate it. Pause if you need to. Come back to me. I end up with u to the 5th over 5 minus 2u to the 7th over 7 plus u to the 9th over 9. Plug back in. Pause it if you need to. Come back to me when you're ready. And I end up with sine to the 5th over 5 minus 2/7 sine to the 7th plus sine to the 9th over 9 plus c. Okay. You guys do this one. It's not as complicated as the last one, but it's very similar, and we will go over this in class tomorrow.